Chapter 4, Binomial Expansion. Lesson 1, Expanding 1 plus x to the n. If n is a natural number, so it's a positive integer, like 1, 2, 3, etc., you can find the binomial expansion for a plus bx to the n using the formula you already know from before. It's as follows. A plus b to the power of n equals a to the n plus nc1 times a to the n minus 1b plus nc2 times a to the n minus 2b squared, and so on and so forth until ncr times a to the n minus r times b to the r, and all the way to b to the n. And that's if n is a natural number. However, if n isn't a natural number, such as a fraction or a negative number, etc., then a different form of the binomial expansion has to be used. When n is not a natural number, the expansion of 1 plus x to the n will be 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed, and so on and so forth. So it will be n times n minus 1 all the way until you get n minus r plus 1 over r factorial times x to the r, and so on and so forth. This expansion is only valid when the modulus of x is less than 1. So minus 1 is less than x, which is less than 1. And in most cases where n is real. Because n is not a natural number, none of the factors of the coefficients for the x terms, n, n minus 1, n minus 2, all the way to n minus r plus 1, none of them are equal to 0. So this version produces an infinite number of terms. However, you can use a finite number of terms to get algebraic and numerical approximations to expansions, and these are more accurate when more terms are used, or when the values of x that you substitute are closer to 0. Let's do an example. Let's find the first 4 terms in the binomial expansion of 1 over 1 plus x. 1 over 1 plus x is the same thing as writing 1 plus x to the minus 1. And so when we expand this using the formula, we get 1 plus minus 1 times x plus minus 1 times minus 2 over 2 factorial times x squared plus minus 1 times minus 2 times minus 3 over 3 factorial x cubed, and so on and so forth. It just wants the first 4 terms. So this is going to be 1 minus x plus x squared minus x cubed, and so on and so forth. The expansion 1 plus bx to the n, where n is not a natural number, is valid for when the modulus of bx is less than 1, or the modulus of x is less than 1 over the modulus of b. This means that you can substitute bx into every x term of the binomial expansion, so you can expand it when it's in this form. Do another example. Let's this time expand 1 minus x to the power of a third until the x cubed term, and state the range of x that the expansion is valid for. So 1 minus x to the third is the same as 1 plus minus x to the third. And so this is going to be 1 plus a third times minus x plus a third times a third minus 1, which is minus 2 thirds, over 2 factorial times minus x squared plus a third times a third minus 1, which is minus 2 thirds, and minus 1 again, minus 5 thirds, over 3 factorial times minus x cubed, and so on. And there's going to be 1 minus a third x minus 1 over 9x squared minus 5 over 81 x cubed, and so on and so forth. The second part says to state the range of x that the expansion is valid for, and so we're going to say the modulus of minus x is less than 1, and the modulus of minus 1 is just 1. So it's the same thing as saying the modulus of x is still less than 1. Let's do another example. Let's expand the square root of 1 minus 2x up to the x cubed term. B, substitute x equals 0.01 to find an estimate for the square root of 2, and C, without any more calculation, suggest how the accuracy to part B could be improved. So for part A, the square root of 1 minus 2x is the same thing as saying 1 plus minus 2x to the half. And so this would be 1 plus a half times minus 2x plus a half times minus a half, which is a half minus 1, over 2 factorial times minus 2x squared plus a half times a half minus 1, which is minus a half, times a half minus 2, which is minus 3 over 2, all over 3 factorial times minus 2x cubed. And this will give you 1 minus x squared over 2 minus x cubed over 2, and so on. This will be valid for when modulus of minus 2x is less than 1, so the modulus of 2x is less than 1, or therefore the modulus of x is less than 1 over 2. B, when we substitute x equals 0.1, we get the square root of 1 minus 2 times 0.01 equals 1 minus 0.01 minus 0.01 squared over 2 minus 0.01 cubed over 2, and so on and so forth. So the square root of 0.98 is equal to 1 minus 0.01 minus 0.000005 minus 0.0000005. And so the square root of 98 over 100 is equal to 0.99495. Remember, these are estimates because we're only using the first 4 terms. So this is going to be the square root of 49 times 2 over 100 is equal to 7 root 2 over 10, which is around 0.989495. So the square root of 2 is around 0.9899495 times 10 over 7, which is around 1.1421421357. For part C, you could say something suitable along the lines of use more terms from the binomial expansion of square root of 1 minus 2x, as that would increase the accuracy of the approximation.